Great. Welcome back to lecture 9. So in the previous lecture, we defined averages over hypersurfaces and with a particular view towards the spherical measure. Now we've done that so we can actually rigorously define the Fourier transform of the surface measure. Recall that Fourier analysis is initially done for, say, Schwartz functions or functions in L1, but these measures on hypersurfaces are not in L1 or any LP. They're only defined, and they're either just regarded as positive measures or as distributions. And so you have to be careful in actually being able to find the Fourier transform. It turns out you can do this, and it's a continuous function. I think maybe even more derivatives than that, and you have some good decay bounds for it actually, which is going to be the starting point for this lecture. In particular, let's take d sigma to denote the induced Lebesgue measure on the unit sphere inside of RD. Okay. We had a spherical measure on each sphere of radius r, and d sigma of r will just mean that it's normalized, so that each of those measures, whatever the mass was defined in terms of, say, the induced Lebesgue measure or as a Dirac delta function, is now normalized so that it's a probability measure. And all of those are related to each other in the way that, so if d sigma r is induced Lebesgue measure, on S of r, the sphere of radius r, let me just write that down. Then so that's induced Lebesgue measure, which I was writing as like d of s. This is actually normalized by the volume of that, which is some dimensional constant. I was calling CD for the volume of the ball. So dCd is the volume of the sphere, unit sphere, and times r to the d minus 1, right? Because it grows like r to the d minus 1 as your sphere expands. This is different from the Dirac measure, which actually grows like r to the d minus 2. Okay. And so equals Dirac measure but normalized by another constant, minus 2. And that was using the homogeneity in defining this. I have omitted that from the current discussion. If we need to, we can circle back to it. Otherwise, it's going to be in the notes for the course. Now, given any one of these, there's a nice relation in terms of the Fourier transform description of the delta measure, which tells you that d sigma r, if I look at his Fourier transform of C, that's going to be d sigma 1 Fourier transformed r of C, where, of course, so the Fourier transform of a measure, when it makes sense, at least, at a point C in RD, is going to be defined as the integral of E x dot C d mu of x. Okay, and this makes sense when you have, say, a Borel measure that has bounded variation. It's integrable in a distributional sense. Right. So sorry, I didn't even really emphasize the theorem yet. So if I look at the Fourier transform of the induced Lebesgue measure on the unit sphere inside of RD, it decays as C goes to infinity. And it decays with a certain power. That is d minus 1 over 2. So d minus 1 here is measuring the dimension of the sphere in a way, and the 2 there is reflecting the curvature, actually. And the fact that it has positive curvature means there's some quadratic differential that approximates it, And that, yeah, we'll see how that comes into play. But this you should contrast with looking at the Fourier transform of the indicator function of the unit ball. Remember, the sphere was just the boundary of the ball, and the ball, we mean everything inside as well. Now that's an honest function, and a L1 function even, and so its Fourier transform is defined in the usual way, which means that you can make sense of it. And it also has some decay. And the decay is actually better than the spherical measure. It's not too surprising. The decay is like d plus 1/2. This right here is usually familiar to analytic number theorists because it comes up in what the Hardy-Littlewood-Wawka theorem. Wawka, I don't know how to say that person's name. When you estimate the number of lattice points inside a big ball. Right. Okay, the higher dimensional versions of the Gauss circle problem. Right. Great. But we won't prove that. That's just a good connection to number theory, and you can use the spherical bound to prove this bound for balls, and then go through the usual majorization and minorization arguments and Poisson summation to estimate the number of lattice points inside a big ball as the volume of the ball plus some error term. So this is, I think, supposed to be starting to do the proof. Hold on. Yeah, okay. Are there any questions at this stage? Any questions about what it means to be the Fourier transform of this measure? All right, I guess not. Let's start estimating it then. Okay, so just to remind everyone, I said that the Fourier transform, d sigma, when I'm not writing the one here, I just mean the unit sphere. D sigma of c for a point C in RG is 1 plus c to the minus d minus 1/2. There are two parts to this theorem. The first bound is when 1 is going to come into play, and the second bound is when c is going to come into play. As we've seen before, the 1 is really going to be a local property of the sphere. It's actually just saying that the sphere is a finite measure. So in particular, I'm going to have the following bound: Fourier transform of E of C, xc, an absolute value. What's the absolute value of the integral? There, which by the triangle inequality, of course, is just move the absolute values inside. And it's just most 1 times d sigma of c. And I could have absolute values here, but that's not necessary because the measure is non-negative everywhere. And we've normalized it so that this is just equal to 1. So we always have this Fourier transform is at most 1 at every point C. Consequently, the theorem is saying that what we really want is some decay as C goes to infinity in any direction. And you might guess that that's going to be the harder part of the theorem, given that this only took a line to do. And that's I'll be spending a little bit of time now. All right, going to my notes. Yes, okay, so we're going to think about the sphere in the following way. First off, the sphere is rotationally invariant, right? It's basically by definition that you can rotate it. Also, from the polar coordinates definition of d sigma, we can see that the measure is also rotationally invariant. Meaning, if I take any little cap and I move that cap around, no matter how I move it around, it's the same cap just transported, it has the same measure, no matter where it is. Any rotation. And a rotation gets you anywhere to anywhere else on the sphere, right? Okay, that turns out to mean that the Fourier transform is also rotationally invariant. So in particular, we actually can say that d sigma hat is rotation invariant. So that is actually equal to just d sigma hat of the absolute value of C. Just depends on how far away C is from the origin. Great, and so we're going to normalize it by just taking C and rotating it to the North Pole. So the takeaway here is only need to prove, let's call it star. Oops. For C equal to 0s and 1, which is, I'm going to write as E sub D. That's the standard, E sub I is the standard unit vector, which is 1 in the ith coordinate and 0 everywhere else. Okay, so all we have to do in proving this is prove that, C is that times some R. Oops. R. So ED times R. Basically, all I have to put here is R ED. And so what I want to show here is that this is just R. And maybe R is a bad choice to do because R you might think of as radius. Let's call it lambda. Great. So that's step 1. Now, step 2 is going to do the following. I am thinking about my manifold as an atlas of charts, and I can make my atlas designed so that, and here's my point ED on it. I take one chart that contains ED, and then I have a whole bunch of other charts. And they overlap a little bit, right? But it's going to be a smooth partition of unity to cover up my sphere. And since the sphere is compact, I only need a finite cover. And I'm going to have one other chart that I'm going to make special, and that's going to be the chart at the South Pole minus ED. So I have this chart. And so I'm going to break up into caps, C1. So this gives me cap C1. This gives me cap C2. And then I have all my other caps. C3, C4, C5, and so on. So I have C3 through CM. But then I have C1 and C2. My two special caps. Great. And I have a partition of unity that maps, say, the same open ball. So I have a ball U in RD minus 1. And I have functions phi I. Nope, I think I say psi I. Which go from, they go from U to each cap, Ci. Okay. And when I do that, I get to write down my measure as this sum. So d sigma is actually a sum of measures, one for each cap. The integral over U of psi I x prime square root of 1 plus, well, actually, it's going to be some AI, which is defining my partition of unity. And then, yeah, 1 plus gradient psi squared. And that's with, of course, dx prime. So that's the integral over the unit sphere. My throat's a little dry. Was I audible just a moment ago?
Yeah, I could hear you.
Okay, good. Okay, now our analysis breaks into, oop, I had an infinity there. It's just m, sorry. So our analysis is really going to break into 1, 2, and many for the different caps. So C1 and C2, and then all other CIs, which are just C3 up to CM. Let's discuss how to handle those right now, the all other ones. Now, since looking at my picture, I have my ball, my blue ball, and these orange ones overlap it. But I'm going to assume that they overlap it in a way that I can actually carve out a smaller ball around the North Pole and the South Pole, such that the orange balls don't intersect at all that ball. In other words, all these other caps are going to be bounded away from the North and the South Pole, and by some amount. Okay, let's call it kappa. So the distance, oops, change my pen back, the distance from CI to plus or minus the North or South poles is always going to be greater than some little kappa, which is positive. And the point here is that when you do this, when you look at this part of you look at the surface measure integrated, right? So I look at the integral over S intersected with the cap CI of AI giving my partition. And I have E of X dot C, D sigma of X. And then this becomes the integral over U AI X prime F of X prime. The square roots, right? 1 plus the gradient F squared, and then E of X dot C dx prime. And the point is that this function here is smooth, because I've chosen a smooth partition of unity. And this function is smooth enough so that when it's multiplied by a smoother thing, it's fine. It's compactly supported. And this exponential, well, its phase is always bounded away. Its derivative is always bounded away from 0. So it's a non-stationary. There are no stationary points, because the only stationary points that come in, remember, C is equal to some lambda times 1 in the last coordinate, but 0 in every other coordinate. Since I'm bounded away from those north and south poles, this thing is always bounded away. It's always non-stationary. And by a higher dimensional version of our previous stationary phase estimates, we get that this is just at most lambda to the minus n for all n. It's just an integration. It's a higher dimensional version of the integration by parts argument. And I'll leave that as an exercise. right? You can use the one-dimensional version by itself and then sort of treat every other coordinate trivially, or you can just treat the d-dimensional version all at once using a higher dimensional version of the operator we defined to prove the stationary phase bounds. Now this worked again because we're on these caps where you're bounded away from zero, from the North and the South Pole. And we have to be left, now we're left with what happens on C1 and C2. And there, okay, I've only stated that this is this sort of decay, right? Minus d minus 1 over 2. And I've proven a bound on the remaining parts that beats that. It's of any order you want. So you are going to guess now that the decay is exactly this on those two caps. And that's going to come from the fact that there is a stationary point that, I mean, the North Pole and the South Pole are stationary points for this phase. That is taking C to B in the direction of the North and the South Pole. Great. Are there any questions so far? Because now the analysis changes to handling the stationary parts. And I've sort of very briefly handled the non-stationary parts. If there's any confusion there, please let me know now. Great. Okay, moving forward. Let's go back and remind ourselves that, okay, so we're going to look in C1 and C2. Looking in C1, oops, C1 or C2. I won't handle C2. It's going to be directly analogous to C1, and that should be obvious once we get through. It's going to be handled very similarly to C1. So looking inside C1, we are actually going to use the implicit function theorem now. To write our coordinates as actually x prime and the square root of 1 minus x prime squared. Right, that's the normal way to think about a chart. Say down here, x prime, and then you have x prime square root of 1 minus x prime squared. And yeah, that of course solves the unit sphere, right? Because I take the sums of squares and I get 1. Good. Now, so this is how we define our chart. And we look, this is my function f of x prime. Let's just look at its gradient, right? Well, the gradient of f x prime is just going to be 1 over the square root of 1 minus x prime squared. As one can calculate. Times x prime. Yes, yeah, I believe I've done that correctly. And what we see is so if I plug in, I need to plug this in near CD, right? Sorry, near ED. But it's this projected coordinate, right? I ignore the last coordinates, right? So ED prime. Well, that's just the prime of this, which is just all zeros. It's a zero vector inside RD minus 1. And you see that f prime set implies gradient of f at 0, which maybe I should write as 0 prime. It is actually just 0 itself, or 0 prime. So it's a stationary point for the phase. For the phase, why am I saying that? I'm saying because we're looking at E of x dot c, which for us is E of x prime, f of x prime, dotted with lambda dd. And so that is by itself a one-dimensional integral, actually. It's E of lambda f of x prime. Cool. And so we calculated that this has a stationary point, this phase has a stationary point at the origin. And we also need to calculate the second derivative. And the second derivative, I won't do the calculation here, but I'll leave you to do it. The Hessian is actually equal to minus the d minus 1 by d minus 1 identity matrix. Which means that, so we have the stationary point, or in other words, a critical point of f, and it is non-degenerate. The gradient, sorry, not the gradient, this Hessian has no zeros inside this little chart about the North Pole or about the South Pole. And now all we need to do is we need to show that this integral, so we need to show that the integral over of E lambda f x prime times 1 plus gradient f. We need to show that this integral decays like lambda to minus 1 d minus 1 over 2 as lambda goes to infinity. And to do this, well, at the moment we have f of x prime minus 0 is going to be x prime dotted with the gradient, sorry, of f at x prime plus basically the Hessian of f at x prime times x prime squared plus some r of x prime, where r of x prime is less than r of x prime cubed. So I should be a little more precise here. I should say that this is x prime and that's x prime transposed, where I've written x as either a coordinate or row vector to make that correct. Great. And before we said that this is 0 in near x, right? So really it's just this part. Okay, and of course I can ignore the 0. And now the question becomes, well, okay, before, if this is the Hessian is just the identity, we have f of x prime is equal to, well, minus x prime squared plus r of x prime. Now previously, oh, okay, I'll write that out actually. That's minus sums of squares plus r of x prime. And we saw in an earlier lecture, I think it was lecture 3, that if you look at the integral of E of lambda x squared smoothed out, dx, and this is just one variable in R. Then we have the principle of stationary phase said that this was at most 1 plus lambda to the minus 1/2. Now we've got, if we could ignore for a moment this remainder term, then what we have is we have a d-fold product of, sorry, a d minus 1-fold product of integrals just like this. And so we get to take this to the d minus 1 power, which would be exactly what we want. So the issue is how to incorporate this remainder term. There are two ways to do that. One is just to appeal to differential geometry and say, I'm going to Morse lemma this, which basically says that there is a diffeomorphism. So it's a refinement of the implicit function theorem that says there's a diffeomorphism that allows you to get rid of this remainder term, and you have exactly this sort of quadratic term. Okay, after you make an appropriate change of variables. And that is whenever you have that the Hessian is non-zero, has no zero eigenvalues. Okay, so Morse lemma is one way to just get rid of the remainder term. And then we use the fact that our, this change of variables isn't going to affect this integral, except for maybe some constant factor. Cool. The second way to handle this is actually to write E of lambda R x prime, right as a Taylor series. And so I've got a sum over j equals 0 to infinity minus 2 pi I lambda R x prime all to the j divided by j factorial. Okay, so the main term to focus on is what's happening here. And we're going to be left with having to consider integrals of the form. So I had some a1 of x prime, which is my my smooth partition of unity on this cap. And then I have e of minus lambda x squared, x prime squared, coming from the fact that the Hessian was minus the identity in d minus 1 dimensions. And then I have lambda r x prime to the j, and this is dx prime. I sum all of this, and I just take those factors minus 2 pi I over j factorial. I just pull them out. So that I really have to care about this sort of thing. Now, when j is equal to 0, that's not an issue. This term is just 1. And we get the asymptotic. We're just looking at the expression we want, which would be this inner part, right? However, when j is bigger, you should be concerned because I now have j goes to infinity. But we're saved actually by the fact that r of x prime, r of x prime is the most x prime cubed. So it has a 0 at 0 of cubic or higher order. It beats that quadratic coming from here. But it turns out, that means when you do the integration by parse arguments, so maybe I should say the following. You have a general lemma that says this. If I take the integral, you want to prove a lemma like this. If I take the integral g of x against e to the minus lambda x squared, dx, I should be primes here, maybe just to make consistent, over RD, RD minus 1, such that, okay, so G is going to be smooth, and say it's Schwartz, so say G is Schwartz, and G of 0 is 0. Then this integral actually has arbitrarily good decay. And that allows us to sum up over J when J is greater than 1, and we only have to care about when J is equal to 0, which is for which we just get to apply the tensor product version of this buddy. So that completes the proof of why the spherical measure as Fourier transform satisfying this level of decay. Just as a couple closing comments on that, there are actually asymptotics which tell you that this is the right order of magnitude as C goes to infinity. And we don't need any subtle any information as precise as that. But it does, it also extends to looking at quadratic things like this. And the theory of Bessel functions comes into play. Yeah, it's all very good stuff, and you can be rather explicit about it in odd dimensions, right? There's a very explicit expression in terms of cosines and just the power of C when you look in 3 dimensions, and then there's a not too difficult one in 5 dimensions, and so on. Great. So I will leave. Are there any questions? Well, let's end there for today then. Thank you very much.